right. Is a tone. Okay, welcome. Thank you to start here at the first hour. And very quickly, I present the first speaker. His invited talk is Gisella Clementini from INAF OAS from Bologna. He have a talk with a large title, a long title, with variable stars in Gaia, with a specific focus on RR Lyrae stars and Cepheids in past and future Gaia dated release. Please.
Thank you.
Use this one. Oh, sorry.
No, this one. Yeah. Good morning, everybody. Oh, okay. So, can you hear me?
Okay, now.
Okay, now.
No. Use this one. Use this one. It works.
Now it works. Okay. Okay. So first of all, good morning to everybody, and it's a real pleasure to be here and in this beautiful city and with this beautiful community. And so I'm very glad and very pleased that and thankful for you that you invited me. Also, it's nice to be here because I can talk of my favorite work, which is the work I'm doing with Gaia, which is kind of very tough work, but it's very rewarding for me. So we'll be talking about Gaia in general, and in particular, I will try to give you an overview of the satellite, on how it is done, and how the observations are done with Gaia, and then I will focus on variable stars and on Cepheids and RR Lyrae. So, where should I point to? Okay, this is the layout of the talk. So, brief introduction on the Gaia mission, then variable stars in Gaia. Why it is doing like this? No? Oh, up there. Okay. Okay, now it's come. It disappeared again. Okay. So let's skip this and go on. So probably, no? Okay, here we go. So just start with Gaia, a brief description. It's an ESO mission. It's a mission all sky, so it observes all the sky without leaving anything left. And it's complete down to magnitude 21. And it measures about 2 billion sources. It provides astrometry, spectrophotometry, and for sources brighter than 17, also spectroscopy. And what are the science topics of Gaia? Study the galaxy in itself. All what we want to know about the galaxy, Gaia is trying to tell us, but also specific objects, like also the galaxy, a map of which Gaia provides a map of the galaxy, but also allows us to study the star formation history in the galaxy, how the galaxy was formed, and then in detail, specific objects, binaries, multiple systems, satellites that are inside the galaxy, and so on, but also, and very important, fundamental physics, because Gaia is a mission that proves general relativity in some way, because it's based, even the processing that is done in Gaia, the measurement of the parallaxes are based on a relativistic model. And most important for what I will talk about today is that Gaia provides the absolute calibration of standard candles that are used to measure distances. And those are the very nice friends, variable stars that are standard candles, Cepheids and RR Lyrae, and tell us, using those variables, also how the Milky Way formed. Brief story of the satellite is an ESA-only mission. It was launched in 2013, is located in L2, in Lagrangian point 2, which is a stable position where it orbits, doing a Lisieux orbit. Sorry for my French, which is not very good. And it took about a month to arrive when it was launched. It took about a month to reach L2, and then there were 6 months of observation commissioning, and then in July 2014, the mission started. The observation of the regular program started. One important point is that the nominal lifetime of the satellite was supposed to be 5 years, that have actually finished in 2017, and 2019, sorry, but there have been 2 extensions. So Gaia, in the end, will be a 10 years mission, which is quite impressive. Very, very quickly, the payload of and Gaia has 2 telescopes, 2 mirrors, with an area of about 0.7 square degrees that are tilted, well, they are fixed on a silicon carbide toroidal structure that you see if I can, there. And they are kept in, with a very fixed angle, which is more than 100 degrees. That is the basic angle that is at the basis of the way Gaia can measure the parallaxes, and also one of the problems of the Gaia mission, because this basic angle that should have been very, very stable, unfortunately, it is not that stable. And so we need to correct, to make a lot of processing of the parallaxes to correct for these basic angle variations. I will not tell more about that, but this is a very unfortunate problem that has caused a lot of difficulties and has needed a lot of work, additional work, but we think we are in good track to control it at least, not to eliminate this variation, but we can correct. The focal plane of Gaia is very fascinating. It's one of the largest ever sent to the space. It has under 6 CCDs, and in fact, Gaia has a part that is used for the astrometry, but also to collect white light photometry. These are 7x9 CCD, 62 CCD. And then there are the 2 spectrographs, where you get spectrophotometry in BP and RP, in blue and red, and where that you can integrate for the photometry, but you also have the spectrum. And then there are the 12 CCD of the RVS, of the spectrograph, this radial velocity spectrometer of Gaia. And with all this stuff, you do astrometry, spectrophotometry, and you have there the spectral coverage, and spectroscopy, both with this is prism spectroscopy, low resolution, or a higher resolution with the RVS, which is 11,000, basically. The star enters from the left, crosses all the CCDs. We also have, a measurement that is also done is the per CCD photometry here, so we can have a photometry that is very quick also. And Gaia is all sky, as I said, and repeats the observation on the sky. And over the 5 years nominal mission, there are on average 70 photometric measurements and 40 spectroscopic measurements. In 10 years, these numbers will be twice. So it's obvious that Gaia is a perfect instrument for variability. And in fact, it does a lot of variability, although it was not really foreseen, or was not the main target, or the main focus of Gaia, or the main goal. Anyway, just to summarize, so we have a all-sky mission where you have almost simultaneous photometry, spectrophotometry, and spectroscopy, low resolution or higher resolution with the RVS. Unprecedented astrometry, because at the end of the game, you get, for the brighter sources, astrometry that is with the precision of the microarsec, 10 microarsec, I should say, to be on the safe side. photometry, which is the millimeg, and then, of course, systematic identification of all the sources all over the sky. The processing is also important because the database is incremental, and for each release, we reprocess all the data. So it's a processing that improves because it's iterative. And the processing is done by the Gaia Data Processing and Analysis Consortium, that is a consortium of about 400, 500 between researchers and software developers that are spread all over Europe. It's a European mainly mission. And you see here the different coordination units that handle the data. So there is a coordination unit that handles the astrometry, one that handles the photometry, the other one that handles the spectroscopy. And then there are those units there that are the ones that use the data once they are processed. And the variabilities is the business of CU7. The data center is in Geneva, and the manager of this data center, well, the leader of the team is Laurent Ayer. Having said that, let's see what Gaia can do with variables. So this is a famous view of the variability tree that was worked by Laurent Ayer and his collaborators. And so you have the different types of variable stars, intrinsic, extrinsic, or also AGN, or sources that are not stars. And in principle, Gaia observes all of them. Of course, for the release that have been so far, you have only some of these sources that have been published, for which the catalog of data have been published. But there are data almost on all these types of sources that will eventually go out with final release. There have been so far 3 releases of Gaia. The first one, the R1 in September 2016, based on 14 months of observations. And these were, the variables appeared for the first time, and that was a very good surprise because variable stars, the variable data problems should have been published in DR4, the release that is in 2025. But, and I'm proud to say that, we had so beautiful data for the RR Lyrae and the Cepheids in the Large Magellanic Clouds that I still remember. I was processing the data. I said, we cannot keep this data for us. We have to put them out. And the Data Processing and Analysis Executive Committee accepted, and they said, yes, let's publish a little bunch of them just to tell the people that Gaia is doing well. And in fact, the first release only contained 3,000 between RR Lyrae and Cepheids. But then in year 2 years later, based on 22 months of observation, there was 500,000 of sources of different types. And in DR3, where you see here, it was divided in 2 parts. EDR3, the early data release 3, where only the astrometry and the photometry was published, the mean photometry, but not the time series photometry. In DR3, 2 years later, based on 34 months of observation, we had 9.5 million variable stars plus 1 million AGN. So the number is increasing. For DR4, we are aiming to have something like, 10 times this, probably. Maybe it's, going from 10 to 100. Maybe it's, a bit too much, but some tens will be there, of millions, of course. And then for those data, we have astrometry, what I've mentioned before, astrometry, G-band, and BPRP integrated time series photometry. But in some cases, we have also released the spectra, the low-resolution spectra, and I'll show you something about that. And the sample in year 3 for RR Lyrae Cepheids also contained a small group of Cepheids and RR Lyrae for which we have released time series radial velocity data. So you have the radial velocity curves. So here, going back to the variability tree, you see highlighted in white the type of sources that have been released in the R3 number, and which means you have the photometry, the time series photometry for all these kind of variable stars. Now, just to complete this statistics, one thing that one should keep in mind is that when we do the variability analysis, we don't select, in principle, the sources. We analyze the time series of all the sources that are observed by Gaia, which means 1.8 billion sources for the R3. So the processing is a huge effort, and we search for variability the whole catalog. And for the R3, there were basically, as I said, about 10.5 million variables between, stars and the AGN, for which we had a median value of 40 measurements, 44 in G, 40 in BP, and 41 in RP. This is the integrated photometry. And on the plot on the right, you have the magnitude coverage, which is from very bright down to all the way down to 21, as promised in a way. And this is the type of variables that are in the R3, is the variability map divided in different types, and you see that the pulsating stars are the highest percentage. Okay, and here are the numbers. Now, for the R3, we have 25 different types of variability, variable published, the ones that I have highlighted in white in the previous slides. And for 11 of them, we have done the special processing, so we have derived the different parameters. Not only period or a classification in type, but also all the characteristics, magnitudes, amplitudes, Fourier parameters, so it's a processing that has been more complete. And now, let's go to the Cepheids and RR Lyrae. Very quickly, the processing, as I said, is, for the R3, is the processing done of all the sources, 1.8 billion, 4 months of observations, and we have used the time series data in G, BP, RP, the RV spectra, the radial velocities, and I've taken into account, of course, also the source astrometry, and in some cases, also the per CCD photometry. So the photometry of each CCD of the astrometric field. Very quickly, the identification of the variables is done using statistical and machine learning methods. There is a classification with the classifier. To each source is given a certain probability of being on certain type of variables. And then for certain types, there is a further processing. Those that are there, highlighted in pink. And for those types, we do a more clear validation of the classification, possibly even a recalculation of the periods, and the characterization of the sources, the full characterization of the sources. So now, I'm sure that you're familiar with this column magnitude diagram. There's a theoretical locus of the old variable stars, and Gaia covers. This is the column magnitude diagram of the R3 that unfortunately you cannot see the movie. Otherwise, you would have seen also these variables doing their cycle, so varying in color for those that are intrinsic variables, or varying only in magnitude for, oops, sorry. This guy. Sorry, I don't know what happened. Spoiling my presentation. Okay. Okay, so you would see some variables that simply go up and down because they are binaries simply. So that's intrinsic, so it's a variability only magnitude, some of them. Or those here, for instance, the long period variables up there, you will see their cycle. So that's very nice. I can give the presentation. If you have a PPT, a PowerPoint, I can give the presentation where the movie, or send you the movie. And this is, for instance, in the same situation, but for the bright part, this is the variable stars in the LMC and the SMC in Gaia DR3. So you start basically magnitude 2021, which is the RR Lyrae in the two clouds, which you are here, and you see that all this part of the diagram is covered, basically. And this is one other movie, very interesting. You have a Myra here, and if you could have seen the movie, you would have seen the star making this kind of excursion in color, while was changing magnitude and color. And this is the RP spectrum, the spectra, I should say, the time series RP spectra of the source that changed due to temperature effect, basically, during the variation, during the cycle of the star. And keep in mind these two peaks in the spectra, because those peaks are very useful. This is a Myra 2000 period, then 2000 years period, and is a carbon or oxygen-rich. It's an oxygen-rich Myra, this one. This is a carbon-rich Myra, 400 days period. And again, you see these two peaks here, but they have a different shape. The different shape of the peaks in the RP spectra allows you to distinguish oxygen-rich from carbon-rich Myra, simply using the RP spectra of Gaia. And that's a beautiful result, because you don't need really to take the spectrum to analyze it. You have the result there simply because you have the time series of the variation along the full pulsation cycle. Cepheids and RR Lyrae, why they are important? Well, I know I'm aware that you all know, but it's useful to repeat maybe. Cepheids and RR Lyrae are the most important stellar standard candles of the cosmical distance ladder. So they set the distance ladder, the first step of the cosmic distance ladder. And also, since RR Lyrae are old objects and Cepheids are young objects, they populate different regions of the galaxy and trace different stellar population of different age. The Cepheids are young, the classical Cepheids, and the RR Lyrae are old. So when you find an RR Lyrae, you know that that system contains an older population. When I say old, it's 13 giga-years old, 10 and 13 giga-years old. When you find a Cepheid, you know that this is a star that is 50 or 500 million years old. So it's a young star. Here, just a brief summary, and I will concentrate here in classical Cepheids that are the most one used for distance scale. Period typically from 100 days, young, and typically metal-rich. They populate the region where there is gas, because these are young stars, so they form where you have gas, and usually gas enriched. This is by metals produced by supernovae or previous stars. And they are important because they are really at the basis of the cosmic distance ladder, because they follow period-luminosity relation. The longer the period, the brighter is the Cepheid, discovered in 1912 by Henrietta Leavitt, and then further confirmed. And this is a more modern, let's say, view of the period-luminosity relation of classical Cepheids, where it is clear that if you move to the near infrared, you go from B to K, the relation becomes tighter, so you can measure the distance better. The RR Lyrae are the fainter cousins of the Cepheids, because they are typically intrinsically 3 magnitude fainter, but they are old. So when you have a system like a globular cluster where you don't have young star, the RR Lyrae tell you something, because you don't find Cepheids, so the distance you cannot get from Cepheids, so you really need also those objects. Even if you are not in a globular cluster, but in a dwarf spheroidal galaxy, you have the same problem. Dwarf spheroidal galaxies are mainly composed from all stars. They don't have gas, so you really need those guys, the RR Lyrae, to measure their distances. And you can measure their distances because they follow a luminosity-metallicity relation in the optical, and a luminosity in a period luminosity relation only in the infrared. And this is the distance scale as it is built. You start measuring distances from parallaxes, and you can do it only locally, because you can measure the parallaxes are typically are angles that are very small. And so you cannot go much farther with the parallaxes. And then you calibrate different distance indicator, and you climb the ladder. And you see here the parallaxes according to Hipparchus, and this where Gaia has brought the parallaxes, the horizon of Gaia for the astrometric measurement of distances. Then, of course, you really need to calibrate the period luminosity relation, the luminosity metallicity relation, the relation that certain standard candles follow, and you can go farther away. And this is exactly what Gaia has done. So this is a summary of what we have in terms of parallaxes for Cepheids and RR Lyrae, and in period luminosity of Cepheids and RR Lyrae. This is the period luminosity in the K-band, so even the RR Lyrae follow. From Hipparchus, using Hipparchus parallaxes, DR1, which was a combination of Hipparchus and Gaia parallaxes for the measurement, DR2 and DR3. You really see a very clear relation, and you have the different types. You have Cepheids or RR Lyrae that pulsates in the fundamental or the first overtone, in red the fundamental and in blue the first overtone. So you really can use this relation, and this is one of the most beautiful results. The period luminosity relation of classical Cepheids in the Milky Way based on Gaia trigonometric parallax, calibrated. And it's coming in. There are about 1,000 Cepheids that have good astrometric parallaxes to calibrate this relation. This is the same for the RR Lyrae. The luminosity metallicity relation in the V band or the G band, the band of Gaia. And this is how the cosmic distal lengths work. Again, you calibrate with trigonometric parallaxes locally in the Milky Way, then you go to systems that contain Cepheids with the Cepheids and supernovae, and calibrate those sources, distances, for instance, in the LMC, in anchors, in systems that contain both systems, and then with the supernovae, you go in the large space where you have the definition of the Hubble constant. And again, this is the same thing. So locally, you have Gaia here, then with relation, period luminosity relation calibrated locally, you go in system like the MLSE intermediate distance, and this is in fact exactly the impact of Gaia, you see, in this part. There were, I think, less than 100 Cepheids here with trigonometric parallax. They are 1,000. And now numbers, just to give you an idea what this catalog contains. In terms of Cepheids, there are 15,000 Cepheids in DR3, of which 900 are new. And in this slide, you have them broken down in pulsation mode and types, because I've mentioned mainly for the distance scale, what is important is the classical Cepheids that here are called DCEPs from the prototype. But you can also have anomalous Cepheids and type 2 Cepheids. And here you have the numbers in different types and in the systems. So the large Magellanic Cloud, small Magellanic Cloud, all sky, which means the Milky Way or small satellites that are inside the Milky Way, but also M31 and M33. Gaia reached magnitude 21, and you can reach the classical Cepheids in M31 and M33 at that level of magnitude. Of course, it's only a small number, only the brightest, but you can reach that far. And in fact, the Gaia DR3 catalog of Milky Way Cepheids is the largest so far, available so far. Light curves, since you are observers, I thought you would enjoy seeing them. These are classical Cepheids on the left and anomalous Cepheids on the right. So G, BP, and RP, light curve. And since these are bright objects, I've selected those bright. You also have the radial velocity curve from the RBS. And these data are all taken simultaneously. So you really have a plus here, because you can do a lot of science with this. Different type, you have also a Cepheid that pulsate in more than one mode. It's a mixture of fundamental, first overtone, or second overtone. And the same for the anomalous Cepheids. And these are type 2 Cepheids, exactly the same, of the different types. So you have all the different types. And now I can anticipate, we also have a large number of Cepheids for which we have, that are in binary systems. So from the radial velocity curve, for it will be published, we have the radial velocity curve and the orbital solution of the systems, because about 90% of the Cepheids are claimed to be in binary systems. And this is a view of the Cepheids in M33 and M31 and M33 that are in Gaia DR3. And as you see, they nicely trace the spiral arms of M31 and also in M33, because they are located in a region of gas where the stars form, basically, because they are young. And in fact, one of the applications done with DR3 was to map the spiral arms with the Cepheids, the spiral arms of our galaxy. So the black dots you see in this plot are all classical Cepheids, and they trace this over-density that is in OB stars and tell you that here there are spiral arms of the galaxy, and this is a comparison with the model. And this tells you also that the model was wrong. The spiral arm is here. And this is coming from this comparison with the Cepheids, open clusters. No, it's not only Cepheids, but Cepheids, open clusters, and OB stars. The same for RR Lyrae. The total number, RR Lyrae, of course, are much larger in number. So they are in the catalog are 270,000, and 70,000 of them are new, basically. And you have them, the number broken down in pulsation type, AB type, C and D, which is a mixed mode pulsation, and where they are. In the LMC, SMC, all sky, which is mainly means the Milky Way, the galaxy, but and in part are in globular clusters and also in some satellites that are inside the Milky Way. And even in this case, they are the DR3 catalog is the largest, most homogeneous, and parameter-rich catalog of RR Lyrae published so far. And one important point is the homogeneity of the catalog, because those data are taken all simultaneously, processed all in the same way. So a lot of systematics is reduced simply because you are treating them as a whole and in the same way. You may be wrong, but you're wrong all in the same way, let's say. And for the RR Lyrae, we have additional products because we can use the Fourier parameters or the amplitude of the light variation to derive information of the metal abundance. And we have used the Fourier parameters to derive the metal abundance for about half of the sample. And the G absorption, the absorption in the G band, using a relation that takes into account the amplitude of the light variation and the color variation. And then we also have radial velocity curve for time series, with the radial velocity curve for 1,000 of them. Light curves, again. Here I'm showing, again, the light curves in Gaia. Now you have BP, G, and RP. And the radial velocity curve on the, this is a C-type, first overtone. This is an AB type, and this is a multimode. This is another IB type. These are the bright ones, because the radial velocity data are available only for sources brighter than 16. But these are the faint end instead. These are about, these sources have only the G band because the BP and the RP, they don't have enough signals. So you don't really have the color, or you have a mean color, but not the epoch color. But those guys are not even in the Milky Way. These are faint satellites that the Milky Way has kind of cannibalized in its process of formation and are around 20.1. I think one is in Tucana. I don't know exactly the name. Oh, yes, this is written down. One is in Tucana, and the other one I cannot read. Probably it's in Phoenix. And this, you wonder what it is. This is a map of our galaxy done by the RR Lyrae. Each point in this map is one RR Lyrae star. Actually, it's not one RR Lyrae star. In some cases, you have a concentration like here and there. These are the two Magellanic Clouds seen through their RR population. And this guy here, this structure you see here, is the Sagittarius dwarf spheroidal galaxy that is merging with, in a process of merging with the Milky Way, and this is the stream of star that she's leaving behind while merging with our galaxy. But there are also other small concentrations here that you can see here and there, and I like the sum of them. These are globular clusters like M3 up there, if I can manage, or M2, M15, omega Sen. So these are, so if you zoom in, you will see many RR Lyrae concentrating there, or small dwarf spheroidal galaxies, Sculptor, Fornax, and others. So this is a real map in RR Lyrae of our galaxy and the system that the galaxy has kind of eaten to form its halo. And this is the same map, but only using the RR Lyrae for which we were able to derive the metallicity. So it's a map, it's half of the sample, it's a map color-coded in metallicity. And you see that, for instance, the RR Lyrae in the two Magellanic Clouds are more metal poor than the RR Lyrae in the central region of our Milky Way. So you can have a map of the system based on their metallicity. And this is also something that was not possible before, because if you were to take a spectrum of each of the sources, measure the metallicity, and you have this now at once, all together, all treated the same way. The metallicity scale can be wrong, but the ranking of one system with respect to the other is correct. And this is the same map, but now in absorption. So you see that, for instance, the regions that are close to the galactic center are the reddening is very high there because you have dust. And so the sources are very much absorbed. While, for instance, the Magellanic Clouds, it's less important, or in the halo, the extinction is less. Now, I'm almost finished. Let's go to the future perspective. We have already had 3 releases so far. The next release, full release, will be at the end of 2025, and is therefore where the data will be based on the results that will be published, will be based on 66 months of observations, which is basically twice what we had with DR3. But before then DR4, it is already scheduled for DR3, another release in the last part of this year, basically, with some specific products that will be released. And something interesting here is that we will publish the radial velocity curves of the long period variables. About 10,000 Myras, semi-regulars, long period variables will be available with this release that will take place at the end of this year. In DR4, it will be published the time series data of everything collected in the first 5 years of observations, 5 years and a half, because the commissioning is also included in the 66 months, which means time series astrometry, time series photometry, time series radial velocity, everything. So it will be, kind of tsunami. And then, again, since we have been extended, we have this doubling of the time. Gaia will go on observing, we'll finish observing, I think, the 10 years, it started in 2014, it's almost, we're almost over, another year of observations. The final catalog that will be published in DR5 is foreseen probably in 2030. And it will be everything. And the expectations are that the astrometry, in terms of, for astrometry, and for astrometry I mean positions and parallaxes, will be better by 30%, but proper motion will be better by 70%, which is important because really you will see how the structure is of the galaxy, how the systems move, the coherence of certain systems, and so on. And then, of course, in the time span that this will happen, there will be also other missions, or actually not missions, but telescope being start operating, like the RR Rubin Observatory and the LSST survey. And LSST will complement Gaia, extending the magnitude limit from 21 to about 4 or 5 magnitudes. And also spectroscopy surveys are planned, and this will start within this year or the next year. And then the future is Gaia Near. It has been proposed to ESA, a new mission like Gaia, but extending the photometry to the infrared. And this is because we want to go to penetrate the region of high reddening of the Milky Way, for which Gaia is blind, because B, V, and G, the optical, it's not capable to go in that region. This has been planned, and there is a lot of, it's a big challenge. It won't be, it will not be probably only a European mission. There will be agreement with NASA or other agencies, space agencies, probably the Japanese space agencies also. I don't know, it's something that is in the making. And finally, something that it's maybe the last interesting thing I want to say you, that based on the data that CO7 has produced for DR3, we have launched a citizen science experiment or work trying to involve the community at large to help us to do the classification, because when you have 10 million sources, 20 million sources, or 100 million sources to classify, validate, it's a bit, it's a kind of a nightmare, I should say. So as an experiment, we have launched this project that is on the Zooniverse platform. You can connect. You get there, it's an ESA-funded project. Anybody can connect, get the data of some, I think so far there are only some types. Yes, Cepheids, eclipsing binaries, RR Lyrae, long period variables, and a few more. You get the data, you can have a look at the data, the period, the light curve folded with the period that we have provided. You can see where, on the color magnitude diagram, those sources are located and where in the galaxy. And then you will not be told in advance what the type of variable is this. You can make your guess. And this is basically the web page you can find. This is, I think it's a Cepheids. Yes, it's a 10-day Cepheids. So you can play your game, and you see. And this is, and it will help us, because, you can also find funny things, or you can detect mistakes, which we will certainly have done. And this is my last slide.
Okay, thank you very much. Questions? One?
Hi, Catherine.
Thank you very much, Gisella, for this wonderful overview. I have a question regarding the classification. You showed the numbers for RR Lyraes, the RREVs, the RRCs, but the RRCs are sometimes confused with some types of binarities with short periods. So, but you have other data. Is this something you can easily discriminate?
Yes, we have, the fact that we have the colors helps a lot. Yes. Because what we do in the processing, actually not exactly in the processing, but in validation, we then, binaries typically are the effect of, two stars that are one orbiting the others. So it's an achromatic effect. Yeah, so if you see, so what we do is to compute the amplitude ratios, and if the amplitude ratio is around 1, that's a flag that could be a binary.
Okay, yeah. Yeah.
While for RR Lyrae, for instance, the typical amplitude ratio is 1.6, 1.7, and for the Cepheids it's similar. So that's one of the things that we do, basically.
Yes, yeah, yeah. Okay, yeah. Thank you.
Yes?
If you have such nice light curves for 100 million variable stars down to a magnitude of 21, are you still interested in amateurs following stars and light curves?
Yes, because we cannot follow them over. I mean, some time you have funny cases where you really cannot disentangle. For instance, what was saying Catherine, you know, if you have a binary contaminants, for instance, or you have light curves that don't fit your idea of a certain type of variable, so you don't know how to classify them. There are certainly cases where doing some follow-up or be able to look each light curve, that would be very important to look, because, you know, for the Cepheids, 15,000, you can really check the light curves one by one. For the RR Lyrae already it's impossible, because I can tell, we didn't manage. For instance, the Ogle team, we know that Igor Sosinski looks to each of the light curves that they publish, but we cannot clone Igor Sosinski to do the same for Gaia, and so it's almost impossible. So that would be something that the amateur astronomer can help. And also, for instance, to follow variation in the periods, variation in strange cases, or something that you cannot explain. That is certainly useful, very useful. So in a way, I would suggest, look at the catalog, see what you find, and compare what you have in your hands and see if you agree, for instance. That's the first thing that you can do also with the with the citizen science experiment. And then, for instance, if your favorite star is not there, ring the bell and tell us, because sometimes in the R1 there was, you know, the prototype of RR Lyrae itself, and it was not in the R1. And actually, it was in the R1, but by mistake it had magnitude 18, which is, you know. So there are cases where the validation would be wonderful if there was a contribution in the validation. In this. For instance, the new sources.
Okay, I follow that Gaia alerts.
Yes, the Gaia alerts is different in a way, because Gaia alerts only triggers alerts of transients, not classical, variables that are not. What the alerts do is to, if you have an event that was not there before, they trigger this, or if they find something that they cannot explain. But all the classical variables, the periodic or even the irregular, but the known ones in a way, they are out of the alerts. They are not alerted.
Yeah, I know. Okay, thank you.
More questions? Yeah.
Hello, thank you. I have a question for you. I've seen one of the first slides that you put. It's related about extrinsical and intrinsical variability. Mm-hmm. I've seen in both cases talks about eclipse. Could you please put an example about eclipse related to intrinsical reasons? Thank you.
Well, actually, probably that's a question. I don't know the exact word. What I can think of is that probably you have in the intrinsic region there, the spotted stars, some of the spotted star could be there. That it's not really a binary, but it's where you have an effect that mimics, in a way, an eclipse, simply because you have the spot, so a dimming of the light. That should be the case. I think, for instance, that case is there. And in the R3, we have some of those sources that have been released.
More questions?
Thank you. If I may, yeah, this for the Blaschko effect. Do you have any interesting observations so far? What can be derived?
Well, there's a story. We have been postponing the processing of Blaschko, well, the identification of the Blaschko from year 1, year 2, year 3, year 4.
Yes.
Simply because we didn't have enough statistics.
I can
because
imagine.
For the, to detect the Blaschko, you need at least, you need hundreds of measurements.
Yes.
So I would say that Gaia is not really for Blaschko, because even in 10 years, you would at most have 140 measurements, and that's not enough.
Yeah.
Although, that now there have been tests, because probably there is something that we can get from the Fourier parameters, some information, there is claim. It's something that we have to, there is a discussion with Laurent Heyer about that, because he would like to push those candidates at least out. And so we are trying to see whether we can say something already in the year 4 using different parameters. But we need to have the data first. We will receive the first data, the year 4 data, the time series with 60 months length at the end of June.
Okay.
Because we cannot even mimic, you see, I have the time series of 34 months, I double it, but that's not the same thing.
No,
we really need the good data to see if it works, if with the Fourier parameters or any other trick we can at least provide candidates.
Yes.
But
yeah.
I would say that Gaia is not really for Blaschko.
No, I can understand.
You have other satellites for that.
No, but I'm very curious to
But
see
we will
what
try.
come out.
If something can be done for the year 4, we will.
Yeah. Yeah, it will give some information
exactly,
at least.
a flag.
Yes,
the idea is probably to give a flag. We will certainly give a flag when the light curve is intrinsically not clean, which can either be multimode pulsation or Blaschko or any other effect like that. That's something that is already planned. We have already changed the pipeline at least for the RR Lyrae and the Cepheids. This is something that we have already introduced in the pipeline.
Yeah, and you can correlate that with metallicity and with the period for so many variables, so it should give some kind of new insight.
Yeah, sure.
Yeah, thank you.
Okay, we have time for only one question more.
Do you have any possibility to check or to give also candidates for binary RR Lyrae?
Well, the story of the binary RR Lyrae has been here for quite a while. I mean, because it's very strange in a way that Cepheids are so often in binary systems and RR Lyrae. So far, there is only one that has been confirmed, Yuma, which has a 23 years old orbital period, though, so the orbital periods are very long. Now, there are claims that there are more, and one of the technique that is used is this light travel delay, but it's only a photometric guess. There is no spectroscopic confirmation. Honestly, I don't know what to say. I try to, there must be a physical reason if the binary RR Lyrae don't exist. But this is something that, it's weird. So there might be there. Now, actually, I should say also something. The RR Lyrae for which we have measured the metallicity, and not only us, but also others, we have found a large population of very metal-rich RR Lyraes, even over solar abundance, which is a bit strange. And it's difficult from the point of view of stellar evolution to produce these RR Lyraes. Because if you think of the globular clusters that are very metal-rich over solar abundance don't have RR Lyraes because their horizontal branch is very, very red. It's very, you cannot populate the stability strip. You don't match. So the hypothesis is that those very metal-rich RR Lyraes are not really RR Lyraes, but impostors that are the result of a binary system of the merging, peeling a star totally, and that's a possibility. Or overflow of matter from one star to the other so that you can enrich it in material. from the stellar evolution point of view, it's very difficult to justify also this population of metal-rich RR Lyrae in terms of binaries. You would need a very high percentage of binaries. So that's the scenario so far, so it's not clear. But there is a lot of discussion, and you know, it's not even very nice, this discussion. It's kind of harsh, I can tell you.
Thank you.
Okay. Thanks again.